For the longest time, we thought the universe was, well, predictable, like a giant clockwork machine. Then quantum mechanics came along and suggested something way, way stranger. And it took one of the most brilliant experiments ever designed to prove just how weird our universe really is. So let's dive into the experiment that basically put reality itself on trial. Okay, this quote right here, it's at the absolute heart of a massive debate. Back in 1935, Albert Einstein and his buddies basically threw down the gauntlet. Their point was pretty simple. If you can know something about a particle without even looking at it, that something must be a real, concrete property. This was a direct shot at quantum mechanics, which was saying that some properties don't even exist until you measure them. So, this really sets the stage for a huge puzzle. And the funny thing is, the person who was most bothered by it was Einstein himself. He helped create quantum theory, but he just couldn't get on board with its weirdest implications. He hated the randomness, the uncertainty. He was just convinced the theory had to be incomplete.
Let's break this down. You've got two teams in this fight. In one corner, there's Einstein's local realism. This is the common sense view. A ball is red, even if you're not looking at it, right? And nothing, absolutely nothing, can travel faster than light. In the other corner, you've got quantum entanglement, which Einstein famously called spooky action at a distance. This idea says that two particles can be linked in such a way that if you measure one, you instantly influence the other, even if it's on the other side of the galaxy. So, how did Einstein try to get out of this spooky mess? Well, he came up with an idea called hidden variables. He thought, maybe these particles aren't communicating faster than light. Maybe they're more like a pair of gloves. Imagine you put one in a box and the other in another box and mail them to opposite ends of the Earth. The second you open your box and see a left-handed glove, you instantly know the other one is right-handed. Not because of spooky action, but because they had that secret instruction from the start. That's what Einstein thought was happening here. For decades, this was just talk. A cool thought experiment, right? A philosophical debate. How on earth could you even test whether these secret instructions were real or not? It seemed completely impossible. But then, a physicist came along who figured out how to put reality itself to the test. And that physicist was John Stuart Bell. In 1964, he did something just incredible. He took this philosophical argument and turned it into actual, testable math. He figured out a way to ask the universe a direct question. Hey, are there hidden variables, or are you really as spooky as you seem? At the core of his work is Bell's inequality. Now, don't get bogged down by the name. Just think of it like this. It's a rule, a speed limit, if you will. If Einstein's common sense view of reality is right, then the universe has to obey this rule. It puts a hard cap on how correlated these particles can be if they're just carrying around secret instructions. A more practical version of this, called the CHSH inequality, boiled it all down to a single number. You run the experiment, you crunch the numbers, and if local realism is the law of the land, your final result cannot be greater than 2. That's it, a clear line in the sand. And here's where it gets good. Here's the showdown. Quantum mechanics, the spooky theory, predicted something completely different. It said, nope, you're going to break that rule. The result is going to be higher than 2. So, you've got two theories making two different predictions. They can't both be right. Someone had to go build this thing and see who would win. Enter Alain Aspect, a French physicist. In the early 1980s, he and his team designed an experiment so ridiculously clever and so precise that it could finally settle the score, once and for all. Okay, the absolute genius of Aspect's experiment was how it closed any possible loopholes. To make sure the detectors couldn't secretly talk to each other, he put them 12 meters apart. A photon would take 20 nanoseconds to get from the source to the detector. But, and this is the killer move, he used a device that randomly switched the detector settings every 10 nanoseconds. Do you see? The choice of what to measure was made while the photons were already in flight. There was literally not enough time for any signal, even one moving at the speed of light, to go from one detector to the other to coordinate the results. Game over for any hidden communication. So this was it, the moment of truth. After decades and decades of debate, the experiment was running. The data was coming in. Would the result be 2 or less, proving Einstein right? Or would it break the limit, proving the universe is fundamentally non-local and just deeply strange? The result came back. It wasn't 1, it wasn't 2, it was greater than 2. Bell's inequality was violated, decisively.
And just like that, the verdict was in. It was unambiguous. The universe does not play by the rules of local realism. Einstein's hidden variables, they don't exist. That spooky action at a distance that he found so hard to believe, well, it turns out it's a fundamental feature of our reality. The universe is non-local.
Aspect's experiment was a total game changer, but it was also just the beginning. As you can see here, it kicked off decades of increasingly sophisticated tests. In '98, they stretched the distance out to 30 kilometers. By 2015, physicists were doing loophole-free tests that closed every conceivable gap. And finally, in 2022, the pioneers of this work, Elaine Aspect, John Clauser, and Anton Zeilinger, were awarded the Nobel Prize they so clearly deserved.
Now, that Nobel Prize wasn't just a pat on the back for settling a 50-year-old debate. It was for proving that this profoundly weird feature of the universe, this spookiness, is real. And it turns out, this is the key to a whole new generation of technology. I mean, think about it. Quantum computers harness entanglement to link their building blocks, their qubits, letting them perform calculations that are impossible for even the biggest supercomputers. And quantum cryptography, it uses this spooky link to create unhackable communication channels, because if anyone tries to eavesdrop, they break the entanglement and get caught. So yeah, proving reality is weird wasn't just a philosophical victory, it's the foundation of a tech revolution. And just when you think that's where the weirdness stops, you'd be wrong. This research opened the door to even more mind-bending experiments. One of them is called the Delayed Choice Quantum Eraser. And this is where things get really, really wild. The full setup is super complex, but the bottom line is just mind-bending. A measurement you make on one particle now seems to retroactively influence whether its entangled twin acted like a particle or a wave in the past. It's almost as if your choice today could change a past event. And that, of course, gets people asking about time travel. But, and this is a huge but, there is no backward in time signaling. You can't send tomorrow's lottery numbers to your past self. This strange pattern only appears after the experiment is over, when you look at all the results and sort them based on the measurements you made. The spooky correlation is real, but causality, it's still firmly intact. Phew. Which leaves us with this final tantalizing question. The quantum eraser doesn't change the past, but it does suggest that the past isn't as fixed as we think. It suggests that what we call reality is a story that's only fully written when all the information from all the entangled parts is finally brought together. And that might be the weirdest and most wonderful lesson of all.